All right, people. So we're gonna do May 2023. So let's just jump right into it. Actually, wait. Let's not just jump right into it. Let me go share this on Facebook and let people know I'm live. Um, did I just send them a Google Meet link? Just sharing it on Facebook. Just give me a chance. Give me a chance, there, all here. So it was a little troublesome to get going. I wanted to start at 11, but a lot of different hiccups was happening. And anyhow, I'm in. I'm in. So good day to all. Can you press like on the stream and share it in your groups and whatnot? Let everybody jump in. Shout out to those of y'all who are from the student hub. I'm seeing like I have 40 persons here with me. I'm really glad for that. Normally the physics lives is less than 100. It's usually less than 100 persons when I'm doing these physics lives, and it's not close to exam. When it's close to exam, we get hundreds. So yeah, so those of y'all who plan on doing physics in the future, you're gonna hang around. This might be interesting for y'all as well. The heater has a power rating of where's my pen? Where's my pen? Read the question. Why I just see if I told y'all everything that could go wrong this morning trying to go wrong right now. But don't worry, the physics must go on. 105 watts. What else? The electrical supply. So it's heating up the water. And all right, so this is a calorimeter. And this is the first question. So we know the first question in physics. We're going to have to draw a graph, right? So this is the temperature. And this is the time. So we're heating it up. Define the term specific heat capacity. So I'll let someone in the chat say that. What do we have for specific heat capacity? Chat. Let me know. Let me make sure this thing is shared. Specific heat capacity is, everybody locked in? We have any physics students here with me? Anybody from the hub? Anybody from my physics class? Or you know what, I can share it with the other physics group. There we go. All right, we have my leak with something here. So those who say it, once it's good, I'm going to use it in the group, in the solution. So Malik, the specific heat capacity C of a substance is the heat energy needed to raise the temperature of 1 kilogram of the substance by 1 Kelvin. Right? So that's good. That's good. Also 1 degree Celsius works as well, since it's just a difference. And then what is this? The formula for energy. So energy, change in energy represents the heat transferred is equal to, well, hold up. This is power. All of the electrical energy produced by the heater is transferred to the liquid, and that power is the electrical power of the heater. T is the time duration. Oh, they want a formula using these symbols. So what is power? And what is power? Power is change in energy over time taken, right? Over T. So energy is P T. So you'll have P T. Y'all catch what I did there? Everybody good there? Because we know this formula, EH is equal to MC change in temperature. So I'm going to use, instead of using EH, they gave me P and T. So that's what they were cooking up here. So power is rate of change in energy. So instead of writing EH in the front, I'm writing PT. And then MC delta, and they're using theta for change in temperature. So this was the little trick with this question. You could have also brought across the T. So you could have P is equal to MC delta theta over T is also correct. But I think this is the better way to write it. Which represents heat energy. Now, to be clear, I would have put where EH is equal to PT. That's to be extra clear, because, there's a reason they give us the P and the T. So, what y'all think about that question? Next one, use the grid. So I have to go find a grid to plot, calculate the gradient, G of the graph. So this usually takes me the longest time to do in class because I have to go and find my graph page. And where's my graph page? Here it is. And then I have to go and plot out all of this. So you're getting to see how I come up with the scale. Usually you get this type of graph. These days they're making the graph with the scale on it already and the axis already labeled. So what we're going to use is we're going to use these values. And they wanted us to plot a graph of what against what. You always want to see what against what. Temperature versus time. So time is on the x, temperature is on the y versus x, right? I'll put my values here for ease of reading. Hi, everybody, tap in. Those of y'all who doing physics, I know a lot of y'all will be watching this in the future. Shout out if you're watching this in the future. Press like. Yeah. I'm gonna draw it. Everybody can try and draw it as well if you have a graph page. And we want, first thing you do is eyeball the graph. So temperature from 25 to 56. Then time from 0 to 360. And time is on the x. So then I go and eyeball my scale and see if this could work. So 0 to 360 would be, let's see if I can use 20, 40, 60, 80, 100, 20, 40, 60, 80, 100, 20, 40, 60, 80, 100. The scale sucks because this is 300 and I need to reach 360. And any other scale will be half of that, so it may finish here. So I may be tempted to do the longitudinal scale. Once again, I do, wait, let me see what they had for us. Graph of temperature versus time. All right, so they had it like this. So we had no choice. They forced us into this idea. They already labeled the axis, so they wanted portrait. Y'all understand what I'm saying? So temperature versus time. So I'm using this graph here, which is the same thing. Let's see what's going on with the, hello, all in new people, Crystal and Camara. We want this to go up to 56, so I can maybe do 10, 20, 30, 40, 50, double that. Maybe the scale and all sucks. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. And I want to go to 56. So I hate everything about this graph. I just want you all to know that because it's not fitting in a nice way, graph of temperature versus time. And we really try to avoid getting stuck with those disjointed scales, those broken scales. Do I need to bring this down to any temperature? No, I just need to work out the gradient. I'm checking to see afterwards. This is the good advice. Always check to see if you have to do anything with the graph afterwards. Usually just find the gradient. There's one precaution. Use your answer, state what is most likely. So something just to state. So it looks like we have no choice. I have to either break the graph, like start from 20, which seems like the best option to get most of the graph used. I can't break this graph. This graph is from 0 to 360. And I can't use 10. So it may seem that I'm forced to use 15 to take up. So I have to use one of the awkward scales. 30, let's see how this will go. 45, 60. And I'll show you what to do if you're forced to use one of these scales. I never really did one on YouTube before. 90, 105. Wait, sorry, I'm doing nonsense. Supposed to be double that, right? So supposed to be 30, 60, let's double check, 90. What is it? Can I get away with 40? 40, 80, 120. What did I check just now? This is 120. I think I checked this just now. 20, 40, 80, 120, 160, 200, 240. This is the one that I checked just now that didn't work, right? 280, 320. So I'm short. So yeah, I'm gonna use 50s. I'm gonna use 50s, which may be not that bad. 50, 100, 150, 200, 250, 300, 350. This isn't as yucky. It's not like 3. It's not like a factor of 3 scale. Like if this is 60, then this gets broken up and you'll get a lot of decimals for each one. It's kind of weird to plot. 350, 400. Everybody cooking. So it actually didn't get too bad of a scale after all. I was getting anxious for nothing. So time in seconds. So I'll show you what to do if you force to break the scale. I also don't think I ever do this on YouTube. And pretend that is the straightest line you ever see. Let's try that again. Right. So I believe if I start from 20, I will get a head start. So I can like start this from 20. And what was I gonna do? 30, 40, so 20, 25, 30, 35, 40, 45, 50, 55, 60. So it works. And then I'll put temperature. I like to write out the whole thing. So I'll put temperature in degrees Celsius. So temperature, comma, I can leave it like that. Temperature theta here in degrees Celsius. And I'll write out the whole thing. Time, seconds. Time is T, right? And that's it. So you write a title, graph of temperature versus time. Temperature, you write out the full thing, degrees Celsius versus time. For time's sake, I just speed in here. And then you want to include a scale as well. So you usually draw the graph first and then put the scale. Or if you feel like you'll forget, just write the scale on the side if you have space, right? But let's draw the graph first so we won't cut through this. I don't know if you all see the points. I kind of have it small here. This is actually the X values. This is the Y. Sometimes you want to write that so you don't make no silly mistakes. 0, 25.3. So 0 lines up with 25.3, guys. Let's see. 25.3 would mean what? So this would be 26, 27, 28, 29. When you choose a good scale, you could usually just figure it out quickly, right? So 26, 27, 28, 29, 30, it works. So 25.3 would just be a little smooch above 25 right there. So it's really good. And 60. So this scale isn't that bad. This might be 60, 70, 80, 90, 100. So the scale works out pretty well, man. I was getting paranoid for nothing. Anyhow, so the 60 goes with 30.5, which will just be a little smooth above, nothing noticeable really at this scale. Because remember, this is 30, this is, just want to make sure, 30, 31, 32. Actually, it is noticeable. It will be in the point above. So 30.5, what we had? We had 60. 60 is on this, and 30.5 is literally on that dot right there. 60, 30 on this dot right here. So that's 30 and each one is 5, so that's 31. So this is 30.5 on the line right there. So we're cooking 120 to the 120 would be 110, 120 is here. So right before this line, and we want 34.9. So really close to 35. So and I'm starting to see my line of best fit forming, so I'm really excited about that. I'm excited about that. I'm drawing my X's a little bigger so you guys can see it. And 180 and 41.2. 180 will probably be 2 less. So somewhere on this line. Yeah, somewhere on this line. And we're looking at 41.2. So 41 is over here. So 0.2 would be a little bad. So about there. So this one feels like it pulls my line a little upwards. But that's okay. That's okay. And that's 180, 190. Yeah, that's okay. 240 and 46. So 240 would be 10 less than this. So 240 is on this line. And we are looking for 46.4. So 45, 46 is one above 0.4. Just be a little smooth underneath this. Are we cooking? I think we're cooking. I think, check all my points. All my points looking good. Have you seen any point that looking wrong? 351.5. 351.5 will look right there. That's 51 and 0.5. And I love everything about this graph. 10 minutes ago, I was like, I hate everything about this graph, but okay, I was paranoid. So 365, last night I got scared with a graph. Those of you all in my physics class, 56.8. That was January. We got a really weird graph. Now, I didn't know about the graph paper. Looked for January, so I couldn't tell. 56.8, 55, 56, 57, so 56.8. The last point always like to misbehave, boy. I'm gonna double check this last point again. 360 is over here. 55. I was wrong. So this is 56 here. Good. 56.8, 56, 57. So 56.8 is a little lower down. All right, so the last point didn't misbehave. I love everything about this graph. And then you want your line of best fit. And essentially, you just want some points below and some points above. A nice little balance. And if you could get some points cutting through the line as well, that's fantastic. That's fantastic. So I'm seeing like most of the points are above and that 1 point below. I'm going to take it now. I'll take it. I could take this. I feel I can live with this. I feel I can live with this. So I have this a bit, this a bit, this a bit. This kind, so these three balance off this one kind of way. Yeah. Well, I think line of best fit looking good. Cooking. And then we need to go ahead and find the gradient. You almost always need to find the gradient. Given that, where's the gradient? Where do we use the gradient, calculate the gradient G of the graph? So once you calculate the gradient, you always need to get the units, right? So what you all think the units is going to be? Those of you all who locked in, what is the units? What are the units going to be? Let me find the, let's find the gradient in the meanwhile, I shall do that. So you want to get a point somewhere down there and a point down there, and you don't want to use any of the given points. So what do I see? I see a point here. I want to indicate the point on the graph. Some people draw the full triangle and thing, which is totally fine. Let's say that this is a point on my graph. Right here. Slightly above it, but I gotta live. And this is, what would this be? In between 50 and 100. So this is 25. 25, that's in between 0 and 25. And 25, 26, 27. 25, 27. 25, 27, yes. So the units for G, what did I leave out? I leave out the scale, which is why I tell you when you remember something, just pay it in one time, just in case you forget it. The scale x-axis stands for every 2 centimeters is equal to 50 seconds. And on the y-axis, what is the scale on the y-axis? Every 2 centimeters is equal to what? 5 degrees Celsius, right? Good. Everybody cooking? Yeah, share it up with your groups and thing now. Tell them. I know a lot of people would be revising on their own. So this is 1 point here. Make sure your point is on the line. Mine looking kind of off the line, but forget that. I just doing this for practice here. And this point here looks good as well. So that's 325. Now remember, you want to take points that are distance away. The triangle must be big. And you could use this, you could do this, and you could do this, and you could do this. And some people like to put this to show x2 minus x1 and y2. You need to go through all of that. Most of the time, they just want you to indicate the points, right? 32.5, comma, what is that number there? That number looks like 51, 52, 50. Dang, I didn't want really what 53.5, but okay, fine, 53.5. So the gradient, G, let's work it out real fast. G is going to be equal to change in y over change in x, which we have come to know. I mean, if you don't know this by now, I don't know what going on with your revision. X, y2 minus y1 over x2 minus x. Because you do this in maths too, right? If you don't know this by now, well, crapo, smoke your pipe, and dog eat your supper. Well, you still have some time. So lock in, lock in. So 53.5 minus 27 over 32.5 minus 25. I think those are nice values. You always want to pick easy to read values. And somebody with a calculator tell me what this is. I don't have my calculator up right now. Hopefully, I'm not forced to use my calculator. Yeah, man, standard 4 student. Those of you who in standard 4, work it out now, man. Tell me what this is. Find a calculator and type it in there. Nobody trying to work all this mentally. What is this? Yeah, nobody trying to work all that mentally, bro. So again, 53 over 600 is the accurate value. Degrees Celsius per second. Thank you, Malik. And what is the rounded off value? So I'll keep the accurate value to use later on. Now it can be 2 point. What? 53 minus 27 over 32 minus 25. Nah, this value looking suspicious by Malik. You sure about that? Yeah, check it over. 32.5. Am I using the right thing? Yeah. I'll make matter without my phone, boy. $53.5 minus 27. So you have 26.5 over 32.5 minus 25. So 7.5. So 7 could go into that about 3 times. Or it was 37, 27. 52.5 minus 27, 32.5 minus 25. So exact would be 53 over 15, right? That makes sense. This is the exact value. We keep enough for later on, right? And then the decimal value is 7.5 out, 32.5 minus 25, 7.5, right? So about 7.07. No. 3.53 recurrent. 3.53. I can put the recurrent to get exact too. Recurrent degrees Celsius per second. Then ask for any specific significant figures. So this is already correct. This is already correct as well. If you round it off, say to why you round it off to, right? And I think we cook in there. We have the title. When you finish with your graph, that'll usually be 30 minutes passing the paper for most students. Oh no, not with the graph, when you finish with question 1. So, but when you finish with the graph, it might be like, what, 20 minutes passing the paper. Look back at your graph, watch it, smile, make sure you don't forget anything, watch your title, and bid it farewell and move on. Okay, good. Given that G is equal to PMC, calculate P over MC, calculate the specific heat capacity of the liquid. So you're not asking no questions where they get that from. G is equal to P over MC. Yeah, that actually makes some sense. And what is the value of P? That must be given, right? Yes, P. and M is 300 grams, which is a little sus. Sus, 300 grams is sus. What do they want? The specific heat capacity. And it looks like they want our specific heat. They give us in stuff in normal kilograms, right? So that M there is very sus. So let me state what we have so far. We have P is 150. Oh, I forget. 105. 105. My bad. So 105, and this is what, so that's good. And then they say M is 300 grams, which is, that's us. So you're going to change that and put 0.3 kilograms. Well done, Malik. And C is what we're trying to find. And what else? G is what we just got as 50 over 7 over 40, 15. 50 over 15 something, so 53 over 15, was it? 53 over 15. 53 over 15. Hey, did I put the units? 53 over 50. Did I put the units when I find the G just now? I absolutely did. Degrees Celsius per second, right? So good. If you don't do that, you're immediately losing a mark in that part of the question, eh? Degrees Celsius per second. So great. And then we just go forth. Well, I would rearrange this one time. So MC is equal to P over G. So C is equal to P over GM, right? Because I want C. C is what I'm interested in. So why leave it there when I could just work with the letters for now? I'll just work with the letters, do a little swappy daps, bring down the M, and I cook it. Make sure you know how to transpose. And then I substitute. So you have 105. Calculator people, don't let me down this wrongs. 53 over 15. And MM is 0.3. And this is supposed to be the heat capacity of the liquid. And they didn't tell us what the liquid is. So I don't think they told us what the liquid is, boy. What is the specific heat capacity? Well, you know water is 4,200. And very few things would have a higher specific heat capacity than water. So you're looking for something reasonable. No. This is CSEC physics. You're allowed to use calculators. 100. That work out a clean 100. Are they sure? Find 100 real low too. Yeah, approximately 100. You get 5250 over 53. 99.05. 99.05. Approximately 100. Well, and yeah, you could use the same units here. This is watts over kilograms. Watts over kilograms degree. Let me just show you how we do this, right? So this is watts over the mass here is kilograms, and we already established that this is degrees Celsius per second. So this second will come back up here. So you'll get watt second kilograms degrees Celsius. But watt second is energy. So you can put joules per kilogram per degree Celsius or per Kelvin, which looks a little neater. So, and this is normally what we have here, right? Joules per kilogram per centimeter per degree Celsius. Joules per kilogram per degree Celsius. And the way to one significant figure equal 100 of that. Let's use Kelvin. Kelvin a little neater than that degree Celsius. 2.1 SF. Yeah, always read back. Take a last read back to make sure there wasn't any wrong enough that you're supposed to do, and you're not going to steal your marks. So I think that was done pretty well. I think that was nice. That was nice. State your things, formula, rearrange first, substitute, answer. Good. Watch out for units. Using the answer calculated in state the liquid that was most likely used. All right, so we could have done something wrong because watch, this is 1700, 3900, 2100, but we get a 100. Highly suspicious work we're doing here. Highly suspicious things. Let's go double check. Let's make sure everything is in the right units. Watts, grams, 0.3, we did change that, so that's good. Specific heat capacity. There was no calculation done here, none here either. I need to double check my change in temperature is fine, and my seconds. Oh yeah, I did some nonsense here. I had 350. I had what, and I put 320. It is 325. My bad, guys. So this is 325 here. Anybody watching this in the future and see that I read 332.5, please note typos could kill you in the exam, right? So watch out for you, or writers. 32. This was 325, and I don't know, somehow it had a decimal point there and I didn't bother to check back. So this is 325. So yeah, we're gonna get a big answer below. So let's change our G. But there was a little thing that helped me to spot the error, so I'm still keeping my marks in the exam so far. What helped me to spot my error? The 100 not making sense. I already know 100 not making sense. So specific heat capacity, you really get things this low. You don't get things this low. So this number is going to change the G. So we're coming back for you just now there, my brother. Coming back for you. So you are getting the 53 over 600. It is getting to 53 over 600. Yep, which is the 0.0883 degrees Celsius. 53 over 600 switches to 0.883 degrees Celsius. So we're cooking. Let's double check to make sure that error didn't transfer into any other thing. No, the next question was literally this one. So what is it? 53 over 600. So we're going to use that 53 over 600 back here, and we're going to get something nice this time. Calculator people, give me a recheck day. Hit me a recheck. 53 over 600. So 105, and you divide it by 53 over 600 multiplied by 0.3. Waiting on the calculator crew here. Units, everything good, so we just need to plug in this. All right, we're getting a 39 from Nicholas. 3962.26. All right. Now in this case, we don't really need to be exact because they wanted the one significant figure. So the one significant figure is who? Again, a clean 4,000 here. A clean 4,000 to one significant figure, right? Cooking. Yeah. All right, now, who is it likely to be? This thing is milk. Well, 3 marks now. A little free 1 mark here because milk is the closest. It was actually a little closer to the 3,900 because it wasn't even clean 4,000. So good. Yeah, everybody good? And that brings us nearly to the end. State one precaution that the class should take in performing this experiment. Don't drink the milk. What is a precaution with this? Let's go back to the apparatus. What is a precaution with this heating coil? So you see the heating element here. We did one like this last night. What we know about this thermometer and the heating element. So a precaution would be, don't let the bulb of the thermometer touch the heating element. This must be suspended in the water. Imagine this is the coil and the stirrer in one. My goodness. Now we're not ending at 12. We ending at maybe more like 1. Depends on how fast the other people. Thermometer should not touch the heating element, or the cup as a matter of fact, heating element, but should be suspended in the water away from the sides of the cup. So that's probably the best precaution I could give there. Okay, so number 2, we out of that question. That question usually should take 30 minutes in the exam. Describe how a wind turbine, it takes us about 30 minutes to describe how a wind turbine, 35 wind turbine produces electrical energy. So this is the question where you're going with change of energy. So wind energy turns propeller blades. This is mechanical energy. Energy in gears and machines. Which turns a turbine. Which turns a turbine. This is the generator. So the wind energy turns the propeller blades. Wind energy passing to the propeller blades will turn the propeller blades kinetic energy So we have EK kinetic energy to mechanical energy in the gears into electrical energy, which turns the turbine generator, which creates electrical energy. How much marks? 3 marks. So I think they want the 3. I think they want EKM, mechanical energy, electrical energy. They want the wind. They want the turbine. They want the blades, the propeller blades, and the one that this is connected to the turbine, and the turbine as you generates electricity. So I will go with wind to kinetic energy of the propeller blades to mechanical energy in the turbines to electrical energy. There's always going to be a question where you're converting energy in the physics exam from chemical to this to that to that to that. So this is that question. Wind energy, kinetic energy, propeller blades, mechanical energy, turbine, electric energy produced. At the end of that. Move on. State 2 advantages and disadvantages of using wind turbines. I'm not waiting on you. So talk fast if you want to talk. State 2 advantages and 2 advantages. Advantages. Right, is renewable, right? Renewable and no pollution. I can elaborate on that. This is state actually. So I give me all these lines. So renewable, no pollution, clean energy. Disadvantages, unreliable. One moment you're getting hurricane force winds in the Caribbean, next moment it's still. Source of energy. Depends on, here you could put abundance of wind in some countries. Unreliable source of energy depends on steady wind supply. And anytime they give you these questions in all of the senses and they say in the Caribbean, you're trying to state things that mean that specific to the Caribbean, right? So maintenance and setup cost is good. and set up course is expensive for a small island budget. And the Caribbean has hurricanes. Destroy turbines. And you have to start back from square one. What are they calling it? Wind turbines, right? Wind turbines. Yeah, it can kill birds, but I don't know how much birds is killed. Disrupt wildlife. So that's the birds. You could do some research. I always hear they talking about turbines kill birds, kill birds, kill birds, but apparently it's not that much. Cars kill more birds than turbines. I don't know. You could research that. But I find these are really good that we have here. Kill birds, Terry say kill birds. Terry say kill birds, kill birds. Terry's a good one. If the mass of the air that passes through the circular area swept out by the turbine blades every second is 8.5 kilograms. Let me read properly. The kinetic energy during this time is 25. Calculate the speed. Well, kinetic energy is half mv squared. And we are given a bunch of things. We were given that the kinetic energy is 2,500 joules, good units. We were given that the mass was 8.5 kilograms. That's all that we was given. So therefore, I can rearrange this formula and get rearrange, and I can get 2ek, bring down the m, is equal to v squared, right? See that? Bring across the 2, it multiply both sides by 2, and then bring across the m. So v is equal to the square root of 2 times the potential and the kinetic energy over m. So now I can just substitute 2 times 2,500. Calculator people, help me out here again. And we get in an answer. Now this answer must be in joule. This answer must be in meters per second. Because we are calculating the speed of the air. And the input power. Now they said every second. Every second this happens. What are you all getting? 24.25. They can't give me much marks for this, right? Input power, 2 marks here because they said every second, and it's just quick maths now. 24.25 meters per second, or 24.3 meters per second if you go to 3 significant figures. So power is always changing energy over time taken. This is one of the main formulas you'll use for power. Another one is P equal IV when you're in electricity. And the energy during this time is 2,500 joules. And the time taken is 1 second. They said 1 second, right? What going on? Acrylics. So this is 2,500 watts. 2,500 watts. It probably was a little tricky question for people in the exam to kind of like, what? How to figure out this power, right? But instead, they did say for every second. So just 2,500 over 1 and you're good to go. And we're moving forward. So the rest of the exam, we're moving pretty quickly through the efficiency of the wind turbine, given that the output power of the generator is this. So this is the input power of the air, and this is the output power of the generator. So efficiency, they love to make you calculate efficiency these days. Make sure you have a little formula for it. And this is if we're doing like percentage efficiency, right? This is equal to the useful energy output over the total energy input. And then you multiply by 100 to get the thing to look nice, right? So you put the 1350 over the total 2,500. It just seems like a little more than half, a little over 1,250. Multiply by 100 and everybody's saying 54%. Cooking. And you get 3 marks for that. Now physics love to give you marks. So another question done. What's up? What's up, Anton? For everybody good. I'll just stop saying soon. I just ask the question one time People saying sir and then waiting 10 seconds to type the question. State two properties of electromagnetic waves. So can travel in a vacuum. Give me some. All electromagnetic waves have the same property as normal waves. So it can be reflected, refracted, diffracted. Yes, it can be polarized. It travels at the speed of light. At the speed of light. C equal 3 times 10 to the power 8 meters per second. They are transverse waves. Good, not enough. Figure 4 shows they wanted to a cup and a string. Describe how the cup and string works. Okay. So when person A, when upper person A speaks, the air molecules vibrate. Well, the key thing here is that sound equal vibration, right? And vibration is sound. Into the cup. I can specify bottom of the cup, which is transferred. Trying to write fast here, but as fast as I talk. The thing is, I don't like to do the papers before. So I'm one of the few teachers you'll see that just do the paper with you. Like I didn't do the paper. I don't even know if I ever do this paper in its entirety, which is transferred to. I should do some questions here and there. Transferred to the string. Which is transferred to the string and vibrates along the length of the string to the next cup. This causes the receiving cup to vibrate and the air in the cup, which can be heard by person B as sound. So the key thing here is sound is vibration. Sound wave causes one cup to vibrate. Long distribution pressure wave travels along the string and races into the other cup. The other cup vibrates and produces sound. Yeah, something like this could work. I like how you use the word wave. The word wave could come in here when you're talking about along the length of the string. It vibrates. And vibrates is sound waves along the length of the string. I like how the use of the word wave here. So, but the key is you want to get vibration, bottom cup through the length of the string, bottom of this cup cause the air molecules to vibrate and you detect that sound. So boom. One of the things for best preparation for physics is whole paper. Physics is one of those subjects whole paper preparation comes in real good. So you sit down with the textbook. You can look up, this is like what, the fourth one of this I'm doing on YouTube. Terry have a few. You can look up Terry too. And you find the paper that we do and you do it for yourself, then you come and you correct it. Then you do it over. You do like about 3 or 4 of those. And then there are some things that you just need to revise off in physics and you need to have the maths good. So you need to have the transposition. So it's either you're failing in one of them, you're not memorizing the laws and the long questions, the 7 marks questions good, or you're messing up the transposition and the maths. Calculate the wavelength of the sound produced by the cup and the string frequency of the sound wave. So this is F. F is 11,000 hertz. And the speed V is equal to the 3 tens meters per second. Well, we know this equation, V is equal to F lambda. So lambda, the wavelength, is equal to V over F. So you're going to put 330 over 11,000, and we're going to get what? And this is going to be in meters. So this is a straight standalone question. Sound cup one vibrate, this vibration, longitudinal suppressive wave travel along the string, reach to the other cup vibrates and cause the air molecules to vibrate. Love that. All that working camera, Malik. I feel all of that could get a little 3 marks too. We get approximately 0.03 meters. Fine. Yeah, I can believe that. 0.03 meters is cool. Describe how the observer can see the coin when the container is filled with water. Right. So remember, the light doesn't come this way. The light goes this way into your eye. So when this is filled with water, light waves, when it reaches the surface of the water, refracts, which means it bends away from the normal since it's going into a less dense medium. So here's how we're going to say that to collect our 2 marks. I think they're looking for refracts, and I think they're looking for bend away from the medium. So I would draw the diagram. If I draw a space there, I'll draw it here with the water, and draw back the coin, draw back this, draw back the refraction, and draw back the eye, right? Draw a line here for normal IR. Cooking. So light from the coin, the light ray from the coin, I'll use ray. The light ray from the coin will now refract away from the normal. The reason it refracts away from the normal is because it's going from since it's going from a more dense to less dense medium, which means angle R is greater than angle I. R is greater than I could work as well. And the ray would be seen, would now be able to be seen by the eye. So the eye can see the coin. Draw the arrow this way. Don't forget that. Okay, cool. The refractive index of the water is defined as the ratio of the speed of light in air. Yes. Calculate the speed of light in the water given that it literally give you the equation. They didn't even have to, right? So air to gas, air to water is equal to, that's refractive index, speed of light in air. So speed of light in air over speed of light in water. I could list all these things that I have. Could come back and do it after the exam too if I was going for speed. Refractive index of water, speed of light in air, speed of light in water, so the speed of light in, so therefore what were we trying to find? What is the speed of the calculated speed of light in water? CW. Let's put just CW since I listed it out, right? Or I could put VW if I want, but since it's light we usually use C. Everybody locked in? Boom. So CW is equal to CA over ANG. So CA was given, yes, 3 times 10 to the power of 8. Great. And this is 1.3. So this is going to be, calculator people help me out, and this will be meters per second. Another 2 marks in the bag. Another 2 marks in the bag. Are you with me here, right? Big up gamer. SCA student passing through, so you should do a video on Jan 2026 physics. I'll be doing that in the crash course. So those of y'all who watching in the future, if you wanna jump in a crash course, the student have the best crash courses. You just simply WhatsApp the number that's running on the bottom of the screen. That 3101306 is running on the bottom of the screen. You WhatsApp that number and you'll be good to go. So 2.13, like people like Malik, I think Nikolai, you in the crash course? 2.31 times 10 to the power of 8 meters per second. They will be there. You could come and see them answer all the questions. 2.31 times 10 to the power of 8. Calculate the critical angle of the water. So the critical angle is what? What we just found. We found the speed of light in water. We have the refractive index of the water. So the critical angle is what? Well, how you find the critical angle? Yes. So N is equal to 1 over sine C. So AW, but we want the critical angle. So I'm going to rearrange this equation. Sine C is equal to 1. Why am I in the crash course by Nikolai? What's stopping it from being in the crash course? So sine C is equal to 1 over A and W. So this is 1 over 1.3 sine C. So C will be the sine inverse of that, which is find outable on your calculator. Calculator people help me out here, and that's going to be a critical angle. Did I leave out anything? Times 10 to the power of 8. Yeah, that makes sense. 2.31 times 10 to the power of 8. Close. It's a little slower in the water. 50.28, 50.3. 50.3 degrees to 1 dp. Is that angle, right? So it's degrees. Moving forward, not degrees Celsius, angle. Draw a label diagram of a thermocouple. How is B? It's have a hot junction. And just going towards a cold junction. Cold junction. And this has some kind of reader here. Let's see. A voltmeter. The hot junction is where it goes in the heat source. Oh, I need to show that these two wires is not the same. Different metal. Now, let me do this a little better. Actually, let me just copy it and show you. So take a pic of this. This is pretty good. This is your cold junction, your reference junction. This is your measuring junction, the hot junction. I like the use of the words here, so you could use this to measure. They didn't say what we're measuring, but usually something hot. You could put this directly in hot flames and thing. And it's 300 per subject. It's 300 per subject. And you have this similar wire. So you want to state this, or you want to say metal type A and metal type B. You want to show that it have different types of metals here. Everybody take down this diagram now. You could just put a normal voltmeter here, and you could use the reading here on the voltmeter to figure it out. I have another way that I see it drawn like this. Similar idea, except that they put the junction in between, the cold junction in between. This is the hot junction, the measuring junction, the different types of wires, cold junction, and this goes to your voltmeter. And voltmeter must be connected in parallel, so you don't kill the circuit. So this actually, I like this one because it's showing like the voltmeter in a parallel situation here. So you can take down one and see which one you like. Just make sure you look like the voltmeter in parallel. and not just directly connected to the circuit. Oh, here's a really simple one that is doing everything. Here's a really simple one that is doing everything. I think this one is simple and it's doing everything. Fantastic. Anything else we leave out here? Reference, heat source, similar wires, metal A, metal B, hot junction. You could remember this is the measuring. This is where you're going to use to measure whatever, and this is the reference. And what happened is metals held at different temperatures will have a EMF, a potential difference between them, and this voltmeter will measure the difference, and yet you can use this to figure out what temperature it is. Cool. So this one's simple to draw, to read. And they've been really loving on thermocouples in these last few years. The thermocouple temperature is used to measure the temperature of the blue part of the flame state trees. Why is that thermocouple better here? Why is a thermocouple better? Why y'all think the thermocouple is better? So basically, one of the advantages of the thermocouple, it's accurate. How would state that? Responds quickly to rapidly changing temperatures. That's a proper change in temperatures. That's thermocouple language runtime. So we see that with thermocouples. Can be used at high temperature. That's thermocouple language again. Can be used at very high temperatures. You can't put your bulb thermometer in 1500 temperatures. Like you're not going to put your little lab thermometer in. So with accurate, I'll use sensitive. It's very sensitive, and it's very sensitive, so increase accuracy. Another reason why thermocouple is really good in the industry is they small, can be placed at blue part of the flame, can be placed exactly in the blue part of the flame. Can break easily. That's not advantage. So it's small. It's like this little thing, this a little hot junction, and you can place that anywhere. You can just set up your thermocouple. It can be, well, in this case, for this application, because in other cases, like in the industry, it could be automated. So somebody don't need to go and keep checking that thermocouple. You could just set that up to a machine and just get readings one time. So all of these work for this situation. And I wouldn't use the automated one for this situation because who cares if you're automated for a candle? It's not like we're trying to measure that candle for the rest of your life. Figure 6 shows a fixed mass of gas trapped kinetic theory. So there's a high percentage chance, like 90%. Class, have you done a paper where they didn't ask anything about the kinetic theory yet? Very rare. Very rare. They love to ask you about the kinetic theory, boy. Oh, God. So make sure you have the kinetic theory. Start off with the kinetic theory and then what they're doing in this one. Trapped gas and pressure. Kinetic theory to pressure. So kinetic theory. What is the kinetic theory? All matter is made up of small particles in a constant state of motion. This motion is a result. The kinetic energy is a result of the temperature. What we're doing, we're changing the temperature. If you increase the temperature, you increase the kinetic energy. You just draw a flow chart or some kind of thing now. I fed up write all these things. So you start off with the kinetic theory. And the kinetic theory, all matter, made up of particles, constant state of motion. And the kinetic energy is proportional to the temperature supplied or the heat energy supplied, the kinetic energy of the particles. And then you want to link this to whatever in this case is You heat it up, we increase. So increased temp equal increased kinetic energy. And then what that doing, boy, you want to come down to the final thing now. So you always start off with the kinetic theory. You go to the whatever you're doing, whether it's increasing the temperature, decreasing the volume, or something you're doing, something related to one of the gas laws. And then, well, pressure. So pressure is force over area. So we need to get like force and area talking about. So you're going to increase on the walls on the piston. So they specifically say piston. So increase collision on the walls of the piston. And then you could use some nice maths, some nice physics to kind of show that's force over area. Increased collision, change in momentum is force. Changing momentum of molecules mean an increased force per unit area on piston. And then you just say therefore whatever, pressure. Therefore, how the gas exerts pressure in the piston. So therefore, pressure is increased on piston. So let's just go through it again because I'm writing real terrible here. The kinetic energy, the kinetic theory, you always start off with the core kinetic theory. You will get a kinetic theory question. So you start off with the kinetic theory. All matter is made up of particles in a constant state of motion. And this motion has, these particles have kinetic energy. And this kinetic energy is as a result of the heat energy applied to the system or the gas or molecules or whatever. Therefore, if we increase the temperature, we increase the kinetic energy of the molecules. That's number 2. And if we increase the kinetic energy of the molecules, we increase the frequency of the collision with each other and the walls of the container, and in this case, the piston, the walls of the piston. That increased change in momentum means an increase in force per unit area, which is an increase in pressure on the pistons. Full marks, 3 marks. They could bring that question and stretch it for 5 marks and thing too. They have done that. You have seen kinetic theory question go for 5 marks. Make sure you know that header coming. Calculate the, well, high chance. Calculate the final volume of the gas given that the final pressure. So pressure part 2 is 1.8 times 10 to the power 5 pascals. Pascals is the proper unit, so we good. Any other thing was given. We have some other stuff here. Let me go and glean it. Which law is this? Who is constant? Who is constant? Fixed mass of gas, which is trapped. The gas has a certain pressure. It's at atmospheric pressure right now. The volume of the trapped gas is this. And the temperature is that. And the electric heater is used to increase the temperature of the trapped gas. It seems like this is allowed to move. The arrows show that the volume could move, temperature can move. The pressure would have to remain the same. No, the pressure changed. So we had to use a full PV over T. We had to use the full PV over T equation. So they had everything changing up. Pressure change. This is the volume, 1.9. Is the volume remaining the same? So usually one of them is kept constant. One of them is kept constant, but I'm not seeing what's the thing we needed to find? Final volume. So yes, the volume is apparently changing. So let's write out all the V1s and V2s. P's and things. So P, V, T. 1, 1, 1. And then P, V, T. 2, 2, 2. So P1 was 1.0 times 10 to the power 5 pascals. P2 was 1.8 times 10 to the power 5 pascals. V1 was 1.9 times 10 to the negative 4 meters cubed. Good units. V2 is what we're trying to find. T1 was, now we need this in Kelvin. So we're going to add 273, right? 27 plus 273 Kelvin. And T2 was 627 plus 273 Kelvin. Class, are we cooking? And gas law states that PV over T is equal to K, a constant, or better written in this situation as P1 V1. Let's put P2 first. P2 V2 over T2 is equal to P1 V1 over T1. Then you substitute everything and go with the grace of God here. Substitute everything, calculator people, get ready to cook. Get ready to cook, calculator people. So all the ones, so we have 1.0 times 10 to the power of 5 over multiplied by 1.9 times 10 to the power of negative 4 divided by 27 plus 7,300. A nice clean 300 here. And we're trying to find V2. So we'll call this. P2 would be 1.8 times 10 to the power of 5 over 627. So that's what? 900. So you will call this whole thing, and then PVT is equal to K, a constant. So therefore, this situation is equal to that situation. So we'll call this whole thing and then multiply by 900 and divide by that, and that will be your answer. Why is I working it out? Let me just let ChatGPT work out the calculation here and see if they can get it before you. Let me get 19 over 300. Give me the calculated volume of the gas. Give me the three significant figures. 19 over 300. Like some of them decimal points are sneaking and mess me up. 19 over 300 meter cube. Everything in the right units, right? 19 over 300. How much I'll get? In decimals. So 0 point something, 0 0.0. All right, 3.17 times 10 to the power of negative 4. 4 negative 4. That'll be negative, right? Negative 4, negative 3. Negative 4, negative 3. Negative 4, 2, 3 significant figures. Okay. Yeah? Everybody satisfied? 3.17. Okay, cool. Cooking. Some random person hand boy. Number 5. State the name of the logic gate represented by the symbol shown in figure 7. That's an AND. If you don't know this by now. And state the name of the, that's a NOT. So some free marks here, right? Some free marks. A little breather. And then this is be the fun part. Anybody's get problems with this? And this is the fun part of the paper here. We did a bit of this in class. Well, we did a lot of this in class actually. So how you list out this? I told you all to just put 0, 0, 1, 1 and then 0, 1, 0, 1 if you have 2. And then watch what C is. C is an OR gate. OR means once you see 1, you're getting 1. So let's do C. C is an OR gate. So once you see 1, you'll get 1. And good. So that's C. We have C done. D is a nut. So D just going to switch everything that's on B. Everything that's on B is going to switch. So 1, 0, 1, 0. That's what a NOT gate does. Logic gates is fun, right? I mean, don't underestimate anything in the exam, but this is almost like playing a little game during the exam. This is cake and ice cream. So E, this is a NAND. And here's how you think about this. Remember, the AND gate only gives a 1 if you see two ones. So that means the NAND gate will only give a 0 if it see two ones. Everything else will be ones. So this is the exception that we're looking for in the NAND gate. Once you see two ones, there'll be a 0. But everything else is 1. So great. That's your NAND gate. But we also need to watch what the inputs are. The inputs are C and D. So we're watching C and D. And we see two ones here. Two ones here. So that will give us 0 there. But everything else will be 1. Understood how we crack that puzzle there, class? And finally, Z is back to being another OR gate. Running out of colors here, boy. Let me try you, my brother. Let me try it. Yeah. So this is our OR gate, and OR gate gives 1 once you see a 1. And this is working with E and C. So once OR gate sees a 1, so this is a useless gate because look how we're going to give 1 for everything. C's, E's. Once it sees a 1, it gives a 1. Everybody understand this? Everybody get this? Are we cooking? I don't know why CXC always do this. This is the second time I see a question and the output is all ones or all zeros or something like that. So this is just useless. Well, what is circuit doing? This circuit giving positive for anything, it's not detecting anything. At least make the thing functional now, right? So figure 9 shows an arrangement. State which material, so soft iron, amateur. I find like this actually this real plenty. Yeah, man, big up all the SCA people. A whole bunch of SCA people just coming here, but we're doing some physics right now, so I don't know if I want to stay and pay attention quietly. List 2 factors which cause an increase in the strength of the electromagnet. More coils, faster movement, something moving, nothing moving. Shocks. So more coils, stronger battery. So stronger battery is kind of vague, so I'll say higher voltage. More turns, more coils, more turns, same thing. What else, boy? Yeah, we can live with them. We can live with them 2 factors. So pretty soon all the syllabus in CXC will change to match this modular approach, but I don't think they will take out or put in much. It will gradually change. There may be some slight minor differences. I'm watching the maths syllabus. Maths is the pilot, so next year maths is going to be different. But you don't have to worry about that. You're in CXC now. State how component X can be used to increase the strength of the electromagnet. So by reduce, that's called a rheostat. Or another name for X is what? Or variable resistor. There were 1 mark, so I don't need to overdo it. But since V is equal to IR, reducing the resistance increases the voltage. Reducing resistance increases voltage, which increases the strength of the electromagnet. That's all. They didn't really make it without your Flemings and thing. Doesn't make you without the Flemings. When you say no Flemings, why? What a waste of time question this is. Like not little not the Flemings, the right hand grip. It's not the right hand grip and North Pole and South Pole, boy. I'll make sure you can do that. No, I haven't done January 2026. I don't know if Terry do it. I will do it in the crash course. I'll do it in detail in the crash course. join the crash course. WhatsApp the number below. There will be a very good investment. Any crash course to join any student is a very, very good investment. When the switch is closed, the reading on the ammeter is 1.5. Calculate the resistance of V is equal to IR. Is this just a V is equal to a case of V is equal to IR? Was there something else I'm missing here? Oh, 12 volts. Haha. So V is 12 volts. I is 1.5 amps. So what is this? Free marks by a little cake and ice cream on the side of the paper here, boy. Yeah, boy. So R is equal to V over I, which is 12 or 1.5. Big up all the calculator people who working out stuff for me. You have a little more to go. You know, this is the symbol for your ohms. And getting them to be a little symmetrical. They're good. So you're looking at 12 divided by 1.5. 9, 8. Yes, 8 divided by 2/3, right? 2/3. Yeah. So 8 ohms. Describe the paths of the alpha particles, beta particles, and gamma particles that pass through electric field. State a reason for each answer. Right, we get into with all the Flemings here. Now, which one are the Flemings? Which one are the Flemings you're going to do to check this? Left or right? Left or right? Are we investigating a motor effect or a generator effect? Yeah, but Malik be knocking on all the questions in math, physics, and maths. We're back at it tomorrow. Tomorrow I'm going to do a paper around the same time. But it's going to be math, so going to have real people here. We're going to be in the hundreds. Should be in the hundreds. Depends on whether I advertise it or not. But just kind of keep it on the mellow for now. We'll jump out in a big way later in April. Or maybe after the crash courses. Maybe you go on the week before the crash courses. Fleming's left or right. So we are investigating. So Fleming's left hand is the motor effect. Fleming's, well, it look like I have the wrong hand up, but the camera doing that, right? Fleming's left hand is the, what I want to say, Fleming's left hand is the motor effect. Fleming's right hand is the generator effect. In the motor effect, the result is you put in electricity and you get motion. And you're investigating where your thumb is pointing. And the generator effect, the result is electricity. You put in the motion, and where is the electricity going to happen? So, what do you think it is? So I can tell you what we have. We have an electric field. Oh, this is actually not Fleming's. This is an electric field. My bad. I thought it was a magnetic field. So if it was a magnetic field, it's Fleming's. So we still ain't get to use Fleming's. So if it was a magnetic field, let me just talk about it real quick because it's supposed to say the left people, right? If it was a magnetic field, everybody watch in case this comes for the exam. If it was a magnetic field and I say this is north and this is south, or sometimes they don't even do the field like that. Sometimes they'll just do the field like this. You all know about this, right? Or maybe they might say it's going into the paper like this. So if it's a magnetic field and you have motion of the particles, this is the conventional current. For example, if it's alpha, that's a positive particle, so that's current, and then you have the magnetic field coming out of the paper. You have to visualize like this coming out of the paper, right? And then you want to find the motion. So the motion will either be this way or that way. So in this case, if you use Fleming's left hand, let me just see if you all can get what that's going to be. Conventional current going this way. Field, it's going to move down. It's going to move down. All right. But it is not a left Fleming situation because it's an electric field. It's an electric field. So this has nothing to do with Fleming's. This is just an easy thing. So which one? The alpha particles. Alpha particles is positive. You think any positive particle want to go up and make the positive stay? No. So I wish they make we draw it easier to draw. I would draw it, to be honest. I'll put it on this idea plus, 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 negative. I will still talk about it, but I'll draw it first. So the gamma going through like nobody's business. The particles actually curl faster. And they will curl towards the positive, right? The alpha particle curls slower because they are heavier. And so you want to say, they want to say which direction they go, and you also with these two, you kind of want to say, you want to show that the beta particles are lighter, right? What do I want? Pass you describe it, right? So deflected towards the negative plate, or the what reason? Since alpha particle is positively charged. And this one is deflected towards the positive plate since beta particle is negatively charged. This one is no charge, so undeviated, right? Very good. And this one, slower deflection than beta because it's heavier. So that's something you could note. What else is something you could note about this? You could note what their particles are. Alpha is like the helium nuclei. Beta is the fast-moving electron. Gamma is electromagnetic radiation. And we are cooking. Why your screen red for me? Are you going to do an AdMaths live here? I had to do something for the AdMaths crew. Must do a little past paper here and there. But normally, the bigger the classes and the student have the more, what is it with? Inclusive they are, or exclusive. So like we do really do the pure maths class, we really have much of those lives. Maybe we could have one sometime. The total mass of the left hand side and the products of the right hand side. Wait, this is the last question? I didn't even really take into account we're going into the last question here, boy. Last 2 pages, boy. Let's just collect this and go our way. The total mass of the particles left hand side and products right hand side. Oh, so they're actually making you work out mass of particles and products. First time they say particles, why didn't say reactants? So, well, I guess particles is a better word. The starting thing. Well, you have one of this and one of this, so 235U92 plus 1 and 0, the mass of particles, would be equal to 3.902, and they give you straight to kilograms. Normally, they give you atomic mass units. Plus 1675 times 10 to the negative 27 kg. So you all just add those two for me, calculator people. Round off nothing else. You don't round off anything in this. If you round off anything in this, you go in and go down a dark and lonely road. And the mass of products. Well, what are we looking at? Anything doubled here, we have 3 neutrons. So we have 1 of the barium. Now you're not looking at the mass number here, you're looking at these things. So again, 3.91875 times 10 to the power of negative 28. I just trusted Malik blindly here. 28. Nah. Check over there. This is 25. This is 25. So check over there. Check over everything. Check over everything. So It's 3.91875 times 10 to the negative 25, right? Yeah, 25, yeah, good. Barium plus krypton 92 to the 6 plus 3 of the neutrons plus, well, nobody care about gamma. Gamma can hold our vibes and a meditation. So barium, we have the 2.289 times 10 to the negative 27. Krypton is 1.575 times 10 to the negative 27 plus 3 times 1.675 times 10 to the negative 27 again. Something spooky about this. How can the mass of krypton be less than the mass of a neutron? Had I error in this paper? Are you with me there? Let me see where's the mass of krypton. Am I missing something? Equation below, fission, reaction. Isn't these supposed to be 25 too? Yeah, all of this should be 10 to the 25. These two is 10 to the 25, folks. I wonder if that was in the official exam, because they're real back now. That has to have been in the official exam. That's the fun. So sorry about that, ladies and gents, but neither my fault. 5, 5. Maybe they sent a paper to fix it afterwards, like I addendum. That is speed and sorry if you see that in an examiner, because yeah. All right, what y'all get? Add it over, you would get something a little different. What we're gonna get if you use 25 here? Just giving you a little time to hit me the answer here, and then of course we need to subtract maybe later on. Maybe that might be the last question. If it happens, I don't know what they will do. They may just abandon the whole question. They never give you free marks in any exam. They never give you free marks in any exam, right? I need to get one of them devices when I'm streaming later on, and when the stream start to pump, like, because these streams will start to reach a 400 and 500 people. I need to get one of them things where I can press the some of them song buttons. Because we need some song buttons for this, bro. Because what is that? How they can leave that error inside it? That is things to make you sweat down the paper. Yeah, what y'all got for this value? Are we actually waiting on this value? 2.289 times 10 to the negative 25, 1.575 times. I don't have any answers to verify it. And 3 times 1.675 times 10 to the negative 27. 3.91425 times 10 to the negative 25. By the way, in the future, if anybody watching this in the future and anything wrong here, notice I didn't really touch a calculator for this whole thing, and that's the live people giving me these numbers. Are we seeing a slight decrease in mass? We certainly are. We certainly are. That's what we're looking for, like a decrease, like in about the 2 decimal place here. And niceties. Mass difference. So the change in mass is equal to, what's the change in mass there, people? 3.91875 minus 3.91425. We almost on the GGs there, which is how much? And then the energy release. So energy release is equal to change in mass, C squared, MC, E is equal to MC. Good. So whatever we get there, we're going to multiply by 3.0 times 10 to the negative 8 to be squared. Don't forget the squared when you're doing this. Tell nobody to double check this part here for you. So yeah. And that's the last part of the question there. Let us see what these numbers are going to be, and we got look to wrap up. Remember to sign up for the Student Hub Crash Course. Any subject you want, add maths, physics, POA, POB, chemistry, biology. If you need to make sure you cover the whole syllabus, link up the crash course. Somebody messaging me on WhatsApp right now. Who's that? Yeah, so we're saying it's 4.5 times 10 to the... So don't ignore me. So is it free? The cash cost isn't free. So 4.5 times 10 to the negative 28 kilograms. Yeah, sorry, this is positivity. My bad. Sorry. Positivity, right? And this is 4.5 times 10 to the negative 28, this squared. So you get like a 16 cancel here, you get like about 11 here. 12, 11. 4.05 times 10 to the power of 11, negative 11 joules. So take note of the kind of answers that you'll be clocking down when you're doing this, because there's a high chance you're going to do one of this in the exam. So that's 2023 there. All in all, it wasn't a bad exam. Most of the questions from after question 1 was pretty good. There was this one error in the paper here. All of this was good. This was good. The electricity part came easy because there's no Flemings. They had a logic gates, and logic gates is 3 marks. What was this? This was unorthodox in that you had to use the full gas law. Very rare you have to use this full setup. But this part was easy. You know you're going to get a kinetic theory. You're prepared for that. The thermocouple is coming. So brace for thermocouple. The light part was pretty easy as well. Some easy refractive. They didn't bring like the whole lens, and you had to draw F and 2F. That's be the worst ones. This was pretty good. Waves here was good as well. Straightforward. So it wasn't a bad paper. A few rough spots, but nothing to make you cry. There was one thing that was somewhere here. What was it? No, I caused that error. I did something weird. Or the scale was a little sus. This left, this y-axis. Other than that, pretty good paper. I foresee people in my class should be able to get 80-90% in this paper, no problem. Sorry, people. What's up the number? Join the crash course. Bigger link. Later will be greater. See you later tomorrow, 11 o'clock. We're going to do some maths. Clock in. We'll do some transformation geometry.